Welcome to the Deep Dive. I'm your host, and today we are going on a highly specific and honestly incredibly valuable mission.
Yeah, hi everyone. I'm excited for this one. We are going to be unpacking a really comprehensive blueprint on how to curate a data set for professional quality image generation.
Right, and specifically doing this on consumer-grade hardware,
Yeah.
using SDXL-based models, because I think a lot of people assume you need a massive server farm to do this right.
Exactly. Or they think, it's just about having a huge amount of data. Like they'll spend 40 hours scraping just thousands of
Oh
images.
yeah, scraping, manually captioning them, renting cloud GPU time, and you sit there expecting this cinematic masterpiece to come out.
And then you hit generate.
Right, you type your prompt, you hit generate, and then the output is just, it looks like melted plastic.
Yeah, the skin tones are like radioactive orange.
The shadows are completely crushed, and the whole image just has this bizarre, I don't know, this artificial sheen to it.
Yeah, so today we're looking at a pretty dense stack of cutting-edge research academic papers, practical engineering guides, that basically prove the problem isn't your prompting. It's
Right.
not your learning rate or, your choice of optimizer. The problem is a mathematical ghost hiding inside your raw files.
Okay, let's unpack this, because this is basically the ultimate masterclass for you, the listener, if you want to move beyond just like amateur prompting and actually start engineering your own professional-grade AI image models right from your home setup.
Absolutely. We're talking about the hidden chaos of color profiles, the mathematics of human perception versus machine learning, and how to actually program a neural network to inherently understand professional color theory.
Which sounds wild, but the sources we have today, we've got research from Stanford on context-aware image colorization. We've got studies on palette-based color guidance and diffusion models, deep dives into pseudo-Siamese convolutional neural networks.
A lot of syllables there.
Yeah, a lot of jargon, but it all points to one undeniable fact. If you don't control the mathematics of your color data, the machine is going to control your output.
Yeah, curating a dataset isn't just dumping thousands of JPEGs into a folder. It's an intricate science of color management, metadata, and semantic alignment.
So think about your own image folders right now.
Yeah.
Do you actually know how your computer is interpreting the colors in those files? Because today, we're going to completely change how you look at digital images.
Yeah, before we even talk about training an SDXL model, we have to look at the raw materials. Because if the foundation is cracked, the model is inherently going to learn those flaws.
Right, so let's start with section 1, the hidden chaos in your raw data. Because if you look at a folder of JPEGs or PNGs you scraped from the internet, you probably think you're just looking at a grid of colored squares.
Most people do. But the source modules we're looking at, specifically the ones on digital images and ICC profiles, they suggest that what you're actually looking at is just a wildly inconsistent soup of contradictory data.
Because, well, let's trace it back. Think about the journey an image takes before it ends up in your dataset folder.
Right. A photograph begins as raw photons hitting a digital camera sensor.
Right.
And that sensor is covered in a Bayer filter.
Which is, what exactly?
It's a microscopic grid of red, green, and blue physical filters. So the camera uses this demosaicing algorithm to basically guess the missing color values for every single pixel.
Right, so right out of the gate, it's an estimation.
Exactly. And from there, the camera's internal software applies a proprietary gamma curve. It applies a specific white balance, and it compresses all of that into a color space.
So if your dataset contains like images from a Canon, a Sony, a mobile phone, maybe a 3D render engine,
You've inherited this massive, completely untracked history of different mathematical interpretations of light.
okay, wait, but let me play devil's advocate here.
Sure?
If I'm using a standard training interface, like Koya, GY, or EveryDream, doesn't the PyTorch data loader just like strip all that metadata away anyway?
It does.
Right. So I always assume that when the script converts the images into tensors, to feed into the AI, it throws out all those camera settings and just gives the neural network the raw numbers. So how is a display profile surviving all the way into the latent space?
Well, the data loader does strip the metadata tag, but that is exactly the problem.
Wait, really?
Yeah, the metadata tag is what tells the software how to interpret the numbers.
Oh, I see.
Yeah. Let's look at the ICC profile, which stands for International Color Consortium.
Right.
An ICC profile defines the absolute boundary of a color space. So, say you have an image in Adobe RGB, which is a very wide color space used by professional photographers, and you have another image in sRGB, which is standard for web browsers.
Okay, I follow.
A pixel value of, say, 255 red in Adobe RGB is a fundamentally different, much deeper physical shade of red than 255 red in sRGB.
Oh.
So when PyTorch strips the ICC tag, it blindly feeds the raw number 255 to the neural network.
And the network now thinks that both of these wildly different physical reds are the exact same color.
Exactly.
So it's basically like trying to bake a cake where half your recipe is written in Celsius and the other half is in Fahrenheit.
That's a perfect analogy.
It's no wonder the result comes out burnt or raw.
Yeah.
By throwing away the map, PyTorch assumes all the coordinates are from the same country. You are forcing the model to calculate an average between two completely different languages of color.
Yeah, because the neural network is a statistical engine, right? It learns the distribution of pixel values.
Right.
So if half your data set is defining color on the wide mathematical scale of Adobe RGB and the other half is using the compressed scale of sRGB, the model's latent representation of color collapses.
It gets confused.
Yeah, it tries to average the variance. And mathematically, that results in that exact plastic, desaturated, or, weirdly oversaturated look you mentioned earlier.
The radioactive orange.
Right. The model hasn't learned a unified theory of color. It's just memorized the chaotic mathematical errors of a disorganized data set.
Wow. Okay, this completely reframes how I look at dataset preparation. Because if you're training a low-rank adaptation on SDXL, and your outputs keep looking overbaked, the text basically suggests the problem might not be your training parameters at all.
No, it's probably the mixed bag of color profiles you fed into it.
So if I'm feeding the model poison, it doesn't matter how good my GPU is.
Right.
We have to normalize the math before the training script ever touches the image.
Exactly.
Well, the practical modules in our sources, they mention using Python libraries like OpenCV and scikit-image to fix this. But what does that actual workflow look like? How do you take 100,000 chaotic JPEGs and force them onto the same mathematical baseline?
Well, you start by writing a pre-processing script. You want to intercept the images before they lose their ICC profiles.
Okay.
So you'd use a library like Pillow to read the embedded color profile of every single image. If an image is in Adobe RGB or, say, Display P3, you mathematically transform those pixel values into a unified target space, usually a linear sRGB space. And you do this using perceptual rendering intents. You're basically recalculating the actual pixel integers so that when the metadata is finally stripped during training, the raw numbers all mean the exact same physical thing.
Okay, so you're translating all the Celsius temperatures to Fahrenheit before you give the recipe to the baker.
Exactly.
And the sources also mention histogram equalization, specifically something called CLAHE. What is the mathematical mechanism there, and why is it necessary for AI training?
So CLAHE stands for Contrast Limited Adaptive Histogram Equalization.
That's quite the acronym.
Yeah, they use it a lot in medical AI, actually. But think about it this way. When an AI looks at an image to extract features, say it's trying to learn the shape of a human face, it relies heavily on contrast gradients.
Right.
If half of your dataset is overexposed and the other half is underexposed, the neural network ends up spending vital computing power just trying to reconcile those lighting differences.
Instead of actually learning the structural geometry of the face.
Precisely. So CLA divides the image into a grid of small tiles. It computes a histogram of the contrast for each individual tile, and it equalizes them locally. But it sets a mathematical limit on the contrast amplification to prevent noise from exploding.
Oh, wow. So it's essentially like dodging and burning the image mathematically to ensure the structural details are evenly visible to the convolutional layers of the network.
Yeah.
We are spoon-feeding the AI the geometry by removing the distraction of bad lighting.
We're providing a stable foundation. But, even after you normalize the contrast and force everything into the same RGB space, you still hit a wall.
Why is that?
Because as the Sciopin paper on convolutional neural networks points out, RGB itself is fundamentally flawed for machine learning.
Let's dig into that. Because RGB is the entire architecture of digital display. I mean, it dictates how our monitors physically emit light, but the research claims a neural network struggles to learn from it.
It really does.
Why is a standard red-green-blue array so hostile to a model trying to learn visual features?
Because RGB hardware design inextricably links brightness and hue.
Bro.
Think of a single pixel in an RGB space. To make that pixel darker, you can't simply lower a master brightness value. You have to independently perform math on the red channel, the green channel, and the blue channel.
Ah.
You're reducing all of them simultaneously just to make it darker.
Okay, so it's basically like trying to turn down the bass on your car stereo, but the only dial you have turns down the vocals, the treble, and the engine power, all at exactly the same time.
Right. The features are completely entangled. In RGB, the luminance, the brightness, and the chrominance, the color, are locked together.
Wow, okay.
So when a convolutional neural network passes a kernel over an RGB image to, say, detect an edge or a texture, a simple shadow across an object completely changes the mathematical values of the underlying color.
Because the RGB values all plummet.
Exactly. So the network has to burn millions of parameters just trying to figure out that a red apple in the shadow is the exact same object as a red apple in the sun.
That is wildly inefficient.
Yeah, it is. Which is why the Stanford CS231 paper highlights a much more robust alternative, decoupling the brightness from the color entirely.
By converting the dataset into the CLab color space.
Yes.
Okay, CLab. Now, I've seen lab in Photoshop, under the image mode settings, but I'd never fully understood the coordinate system. How does breaking an image into lab fundamentally change what the neural network is looking at?
Well, CLab is designed around the opponent process theory of human vision.
Okay.
Our eyes don't actually perceive red and green simultaneously in the same location. They oppose each other.
But you never see a reddish green.
Exactly. And CLab maps this mathematically into 3 dimensions. The L channel contains exclusively the lightness data, so ranging from absolute black to absolute white.
Okay, so that's the brightness completely decoupled.
Right. Then the A channel is an axis representing green in the negative direction and red in the positive direction. And the B channel is an axis representing blue in the negative direction and yellow in the positive direction.
So if I isolate the L channel, I'm just getting a highly detailed grayscale image of the structural lighting.
Yes.
And if I look at the A and B channels, I'm just looking at floating color data without any shading.
Which is exactly what a neural network wants. By feeding the AI an image in the LBAB color space, the convolutional layers responsible for edge detection and texture mapping can focus entirely on the L channel.
Without being confused by hue shifts.
Exactly. Meanwhile, the layers responsible for color distribution can learn from the A and B channels without being confused by shadows or highlights. You've just drastically reduced the computational friction required for feature extraction.
That is incredible. But wait, if CLab is the holy grail of decoupled color spaces, why did the SciOpen paper ultimately conclude that a different space HSV-FOL yielded the best performance in their ablation experiments?
Yeah.
Like, what is the mathematical distinction between L and HSV-FOL?
Well, what's fascinating here is the sheer scale of the empirical tests the SciOpen researchers ran. They used architectures like LINET5, AlexNet, and MobileNet across multiple color spaces.
Like Lab, YCBCR, LUV, XYZ.
And HSV-FIFOL. Now, HSV stands for hue, saturation, and value. And like LWUB, it isolates brightness, the value, from the color information.
Okay.
However, while ELBO calculates color on opposing Cartesian axes, like an XY grid HSV maps color on a cylindrical coordinate system.
Like a cylinder.
Yeah, the hue is the angle around the cylinder, and the saturation is the distance from the center.
And what about the FUL designation?
Right, so standard HSV often compresses the hue angle into a smaller 8-bit integer range, like 0 to 179, just to save memory. Yeah. But HSV at eFUL utilizes the entire mathematical spectrum of the space. And the researchers found that for specific complex datasets like CFAR 100, which has 100 highly diverse classes of objects, and NTL 10, which uses high-resolution images, the cylindrical mapping of HSV full actually allowed the network to generalize color relationships slightly more efficiently than the Cartesian mapping of L.
Interesting. But how did they actually feed this into the network? Like, did they just convert all the JPEGs to HSV full and train a standard model?
Yeah. No, they used a much more advanced architecture. It's called a pseudo-Siamese convolutional neural network.
Okay, wait. A Siamese network usually implies 2 identical networks analyzing 2 different inputs to find a similarity score, right? Like how facial recognition works.
Exactly.
So how does a pseudo-Siamese network operate on color spaces?
Well, in a standard Siamese network, the 2 branches share the exact same weights. But in a pseudo-Siamese network, you have 2 parallel neural network branches with the same architecture, but their weights are allowed to update independently.
Okay.
So the researchers fed the standard RGB version of the image into branch A and the HSV full L version of the same image into branch B. The 2 branches process the spatial hierarchies independently.
Ah. So branch A is fighting through the entangled lighting and color of RGB, while branch B is smoothly extracting structural features from the decoupled HSV space.
Right. And then deep within the architecture, usually right before the fully connected classification layers, the output feature maps from both branches are concatenated.
They're stitched together.
Literally stitched together mathematically. The network synthesizes the raw hardware-level color data from the RGB stream with the highly perceptual, decoupled structural data from the HSV stream.
And that fusion is what enhanced the recall accuracy.
Drastically.
And honestly, what blows my mind is the hardware section of this study. You hear about dual-branch pseudo-Siamese network architectures, and you assume, like, oh, this requires a server farm in Silicon Valley.
Yeah, millions of dollars of compute.
But the source material explicitly states the researchers ran these ablation experiments on consumer hardware.
Yeah, they utilized an AMD 3500X processor paired with an NVIDIA RTX 3090. And for the later aesthetic models we'll talk about, an Intel i9 with an RTX 4090.
That is hardware you can literally go buy at a local electronics store right now. It completely democratizes dataset engineering. The bottleneck for creating a professional model isn't VRAM anymore, it's math. If you write a Python script using OpenCV to convert your dataset into HSV FIFOL and structure your PyTorch training loop to utilize a dual-branch input, you are squeezing performance out of a desktop GPU that rivals unoptimized data center training.
It is entirely about data efficiency.
Okay, but even with perfect data efficiency, we still run into the next massive hurdle of dataset curation.
For sure.
Let's say you've downloaded 100,000 images, you've normalized the ICC profiles, you've equalized the histograms, you're ready to convert them to HSV FIFOL. But a massive percentage of those images are just going to be fundamentally ugly.
Yeah, a lot of garbage data on the internet.
Right. They might be blurry, poorly composed, or just aesthetically displeasing. And you cannot manually look at 100,000 images to decide what belongs in your elite training set. You'd lose your mind.
You really would.
So we need a way to mathematically calculate beauty, which sounds like a paradox. How do you program a machine to assess something as subjective as aesthetics?
Well, the short answer is, you don't program it with rules. You program it to emulate consensus.
Consensus.
Okay.
Yeah, we draw on the paper titled AI-Driven Art Learning System, Automated Color Assessment Through Image Recognition. And this introduces a framework known as the HSV NEMA network.
Now, NEMA stands for Neural Image Assessment, correct?
Correct.
How does the architecture of NEMA differ from just a standard image classification model?
Okay, so a standard image classification model like ResNet or VGG16 looks at an image and tries to output a binary classification, right? This is a cat or this is a dog.
Yeah, 1 or 0.
And it uses a loss function like cross-entropy to measure how wrong it is. NEMA fundamentally alters this approach. Instead of a single classification, the final fully connected layer of the NEMA network is replaced with a dense layer of 10 neurons.
Okay.
And these 10 neurons correspond to human rating scores from 1 to 10.
So it's predicting a score. But beauty isn't a single number, right? I mean, two humans might both think the image is beautiful, but I give it an 8 and you give it a 9. How does the math capture that subjectivity?
That is the genius of NEMA. It does not predict a single mean score. It uses a softmax activation function to output a complete probability distribution across all 10 buckets.
So it's spreading the bet.
Exactly. It might say there is a 10% chance humans rate this a 7, a 60% chance they rate it an 8, and a 30% chance they rate it a 9.
Wow. It predicts the curve of human opinion.
Right. And to train this, the researchers had to abandon standard loss functions. They utilized something called Earth Mover's Distance, or EMD.
Earth mover's distance. That sounds very industrial.
It's a great visual, actually. EMD mathematically measures the cost of turning one probability distribution into another.
Okay, walk me through that.
Say the true human consensus was a tight bell curve around the score of 8, and the AI predicted a bell curve around the score of 4. The Earth mover's distance calculates the work required to physically move the mass of the prediction curve over to match the true curve.
Ah, I get it. It's pushing the dirt from one pile to another.
Exactly. By minimizing this EMD loss over thousands of epochs, the AI learns to inherently mimic the nuanced distribution of human aesthetic judgment.
That perfectly explains the mathematical mechanism, but, an AI is only as good as its ground truth data. Where did they get the true human consensus to train this in the first place?
They utilize the AVA database aesthetic visual analysis. It contains 255,530 images.
That's huge.
It is. And crucially, each one of those images was subjected to peer review by an average of 210 human photographers and artists.
Wait, really? 210 ratings per image?
Yeah, resulting in this incredibly rich statistical distribution of scores for every single file.
Over 250,000 images, each judged by 200 people. That is an incredibly robust baseline. And the researchers modified the standard NEMA architecture to operate using the HSV color space we discussed earlier.
Yes, so the HSV NEMA model feeds the hue, saturation, and value data into the convolutional backbone, and the results were striking. When predicting the human aesthetic scores of the AVA dataset, the HSV NEMA model achieved an 80.84% accuracy rate.
Wow.
It also performed phenomenally on a custom, highly colorful dataset of flowers, hitting 81.69% accuracy.
Okay, but what happens when the network encounters actual garbage data? Because this study mentions they tested it on the TID 2013 dataset. What is that?
TID 2013 is a dataset specifically designed for image quality assessment, and it is heavily polluted with 24 distinct types of distortions.
Like what kind of distortions?
We are talking about severe Gaussian noise, heavy JPEG quantization, and chromatic aberration.
Okay, let's define chromatic aberration for a moment, because it's a perfect example of what ruins datasets. Computationally, what is it?
Chromatic aberration occurs when a physical camera lens fails to focus all colors to the exact same convergence point.
Because the glass bends the light differently.
Exactly, because different wavelengths of light red, green, blue bend at different angles through the glass, you end up with color fringing along the high contrast edges of an image.
Right, you'll see like a distinct purple or green halo around objects.
Yeah, and mathematically, it completely corrupts the spatial alignment of the RGB channels.
So when the HSV NEMA model looked at these heavily distorted, mathematically corrupted images in the TID 2013 dataset, how did it react? Did the Earth mover's distance loss just skyrocket?
Well, the accuracy dropped to 79.37%, but more importantly, the researchers analyzed the model's predictive confidence.
Okay.
By looking at the variance of the predicted probability distributions, they saw that the AI was highly confident when assessing the clean AVA images, but statistically uncertain when assessing the distorted TID 2013 images.
The distributions just flattened out.
Exactly. The network could not confidently find the aesthetic value because the underlying structural math of the image was destroyed by the distortions.
Okay, listener, the implication here for you at home is massive. What stands out to you? You don't have to manually curate your dataset anymore.
No.
You can take this open source HSV NEMA architecture, load it onto your local GPU, and literally point it at your folder of normalized images. You script it to calculate the predicted mean score from the distribution for every image and automatically delete any file that scores below, say, a 7.0.
It's brilliant.
You are employing a mathematically rigorous, tireless AI art critic to prune the bottom 80% of your dataset, ensuring your final SDXL model only learns from top-tier, color-stable aesthetics.
It is the ultimate quality control filter, but, and this is a big but, even if you have a folder containing 10,000 aesthetically flawless, perfectly normalized images in a decoupled color space,
Let me guess. Something else breaks.
your SDXL training will still fail catastrophically if you ignore the semantic layer. Because SDXL is a text-to-image diffusion model. The model does not just memorize the pixels, it maps those pixels to the language provided in the caption.
Right, so if the visual data is the paint, the text captions are the brush. If you have a breathtaking picture of sunset, but your automated scraping tool just tagged it with the one-word caption sky, the model is never going to learn how to associate those complex orange and violet HSV values with the actual word sunset.
Exactly.
To understand how vital this semantic mapping is, we have to look at the Stanford CS2301N paper on context-aware image colorization.
This paper provides an absolute masterclass on how language influences latent color representation. The researchers built a convolutional autoencoder designed to take a grayscale image and predict the missing color channels.
Okay, let's break down that architecture for a moment. How does an autoencoder predict color?
It typically uses a U-Net-style architecture.
Okay.
The encoder portion takes the grayscale image, which, remember, is essentially just the L channel of the L-able color space, and runs it through a series of convolutional layers and max pooling operations.
Shrinking it down.
Mathematically shrinking the image down into a dense, highly compressed latent representation. This captures the high-level geometric features, like it knows it's looking at a car, a tree, a face.
Right.
Then the decoder portion takes that compressed geometry and uses transposed convolutions to upscale it back to the original resolution, predicting the A and B color channels at each step.
So it's filling in the blanks.
Right.
And the Stanford team trained a baseline model using only this visual process,
Yeah.
right? No captions at all.
That's right.
How well did it colorize the grayscale images?
Very poorly. The paper notes that without semantic context, the model made conservative guesses.
Meaning what?
Well, because the network only sees the geometry of a car in grayscale, it doesn't know if the car should be red, blue, or silver. Mathematically, the safest way to minimize the loss function during training is to just predict the statistical average of all cars it has ever seen.
Which results in that muddy, desaturated, grayish-brown look.
Exactly.
It's the hallmark of early AI generation. The AI is terrified of committing to a bold color because it lacks the mathematical confidence to stray from the mean.
Precisely. So to solve this, the researchers introduced language. They used the Flick 30K dataset, where every single image is paired with 5 highly descriptive human-written captions.
Okay, but you can't simply feed raw English text into a convolutional neural network.
No, you have to translate the text into numbers using an embedding model.
And they tested 2 specific language models here, BERT and CLIP.
Yeah.
Let's explore why BERT, which is arguably one of the most powerful natural language processing tools ever created, was fundamentally outclassed by SCLIP in this visual task.
Well, BERT stands for bidirectional encoder representations from transformers.
Right.
It is trained on masked language modeling. You hide a word in a sentence, and BERT guesses the word based on the surrounding text. It understands the grammatical syntax and dictionary definitions of words exceptionally well.
What?
But BERT operates entirely in the realm of text. When the researchers extracted the BERT embeddings of the captions and concatenated them into the bottleneck of the autoencoder, the colorization improved, but it still struggled with spatial color relationships.
Because BERT knows that the word apple is often closely related to the word red in a sentence, but it has absolutely no idea what the geometric shape of an apple or the physical wavelength of red actually looks like.
Right, it is blind.
So how does CLIP solve that?
SCLIP, which stands for Contrastive Language Image Pre-training, is trained on a fundamentally different loss function. It uses contrastive loss across massive batches of text-image pairs. In a training batch, CLIP calculates the text vector for a caption and the image vector for the corresponding picture.
And a vector is just an array of numbers pointing somewhere in high-dimensional space.
Exactly. It then computes the cosine similarity between every text vector and every image vector in the batch.
And cosine similarity being a mathematical measurement of how close 2 vectors are pointing in that multidimensional space.
The contrastive loss function forces the model to maximize the cosine similarity between the correct text-image pairs, so along the diagonal of the batch matrix, while aggressively minimizing the similarity of all the incorrect pairs off the diagonal.
Oh, wow.
So over millions of iterations, CLIP builds a shared latent space where the mathematical geometry of the text vector for red apple occupies the exact same coordinates as the visual vector for a picture of a red apple.
It builds a mathematical bridge between the dictionary and the optic nerve.
Yeah.
So when the Stanford researchers concatenated the CLIP text embeddings into the bottleneck of their colorization autoencoder, what happened to the muddy conservative colors?
The mean squared error, or MSE test loss, plummeted to 0.0106.
Incredible.
The model stopped guessing and became highly decisive. Because CLI provided the semantic context telling the model, this is a red Ferrari, the decoder could confidently predict the extreme values in the A and B channels required to generate that specific shade of red. The model knew exactly what it was looking at.
And this brings us directly back to engineering a dataset for SDXL. Because SDXL uses CLIP embeddings to guide its entire generation process.
It does. When you enter a prompt into Stable Diffusion, the CLIP text encoder translates your words into a sequence of token embeddings.
Okay.
The unit architecture, which is actually doing the denoising work to create the image, relies on a cross-attention mechanism. It constantly queries the CLIP embeddings, asking, where should I put the red pixels to satisfy this text condition?
So if your dataset was trained with lazy, auto-generated captions that lack specific color descriptors, you've completely destroyed the mapping.
Yeah, you are fundamentally teaching the unit to associate random noise with your aesthetic goals.
The text is just as critical as the pixels. Every image in your dataset needs a descriptive, CLIP-aligned caption that explicitly details the lighting, the mood, and the exact colors.
Absolutely.
But honestly, even if you write the most robust caption imaginable, natural language still feels inadequate for professional color management.
How so?
Well, the word teal is statistically noisy. It could mean 100 different shades. If a professional graphic designer needs to train a model to output a specific brand identity, typing words into a prompt will never be precise enough. We need a way to mathematically force the AI to respect an exact color palette.
Which brings us to the bleeding edge of diffusion control. We look at the paper titled Exploring Palette-Based Color Guidance in Diffusion Models.
Okay.
The researchers realized that relying solely on the CLIP text encoder to interpret raw color data is a dead end.
Wait. Here's where it gets really interesting. Why not just type the exact RGB code into the prompt? If I want a specific blue, why can't I just prompt a sports car? RGB 01222 255.
The researchers empirically tested that exact method, and the network collapsed.
Really? Why?
Because the CLIP text encoder is a language model optimized for semantic text. When it tokenizes a string of numbers like RGB 0, 122, 255, it splits it into arbitrary subword tokens.
Oh, it doesn't see it as math.
Exactly. It completely loses the mathematical meaning of numbers and tries to interpret them as abstract language.
So it's like reading coordinates to a poet.
Basically, the UNet receives garbage cross-attention data, resulting in chaotic color artifacts and completely unintended hues. You cannot feed raw math into a language encoder.
So if we can't type the hex codes into the prompt and we can't rely on adjectives, how did the researchers build a system to mathematically steer the diffusion process?
They had to build a parallel conditioning architecture. First, they constructed a massive custom dataset ccalled LAION22K PTI.
PTI standing for palette text image.
Correct. For all 22,783 images, they mathematically extracted the 5 most dominant colors to create a rigid ground truth palette.
Okay, but how do you algorithmically determine the 5 dominant colors of a highly complex 4K photograph? You can't just take the average, or you just get gray.
They used k-means clustering,
Yeah.
and they executed it specifically in the Scilab color space.
Okay, walk us through the math of k-means clustering on a pixel level.
All right, you map every single pixel of the image as a 3-dimensional coordinate in the LAB space, based on its L, A, and B values.
So you have millions of dots floating in this 3D space.
Yes. You then randomly drop 5 centroids, think of them as points of gravity, into that 3D space. The algorithm calculates the Euclidean distance from every pixel to the nearest centroid, grouping them into 5 clusters.
Okay.
Then it calculates the mean mathematical center of each cluster and physically moves the centroid to that exact center.
Oh, I see.
And it repeats this process, calculating distances, moving the centroids over and over until the centroids stop moving.
Because they've settled into the perfect gravitational center.
Exactly. Those final 5 coordinates represent the absolute mathematical centers of gravity for the colors in that image.
That is beautiful. It is an algorithmic distillation of the image's soul.
It really is.
So now they have a data set where every image is paired with its caption and its mathematically perfect k-means palette. How do they inject that palette into the diffusion model without using the text encoder?
They developed a separate palette representation model designed to learn palette embeddings. They tested 3 different architectures. A model that only looked at the palette, a model that looked at the image and the palette, and a model that fused the text and the palette.
And obviously the text palette fusion model won.
It did.
But I need to challenge this.
Go for it.
Why does the AI need a text caption to understand a mathematical color palette? Why can't it just look at the 5 hex codes and paint the picture? Isn't that the whole point of bypassing the language model?
Because color application is entirely dependent on semantic context.
How so?
A palette of deep reds and dark browns implies a completely different application if the text prompt is a rusty abandoned tractor versus a fresh red velvet cake.
Oh, yeah, obviously.
The UMet needs to know where to route the color spatially. To teach the model this relationship, the researchers utilized masked color modeling.
Like the masked language modeling we discussed with BERT, but for colors.
Exactly. During training, they treat the 5-color palette like a sequence of tokens. They randomly mask or hide some of the color tokens. The neural network must analyze the unmasked colors, read the text caption, and mathematically predict the exact lab values of the missing colors.
So it's learning to fill in the blanks, but with exact color science.
Right. And by penalizing the model when it predicts the wrong colors, it forces the network to learn an incredibly deep internal representation of how specific palettes interact with specific semantic concepts.
That is brilliant. It forces the AI to learn color theory in context. So when it comes time to generate an image, how does this palette embedding actually talk to the UNet? Do they just concatenate it with the CLIP text embeddings?
Yes. The learned palette embeddings are fused with the text embeddings. The UNet's cross-attention layers are modified to accept this concatenated tensor.
Oh, yeah.
The text tells the UNet what to draw, and the palette embedding dictates the exact mathematical boundary of how to color it. It provides an absolute constraint on the latent diffusion process.
But wait, why is this better than just using something like ControlNet?
Well,
People use ControlNet all the time to force the AI to respect line art or structural poses.
Yeah.
Couldn't you just use a color-based ControlNet?
Well, ControlNet is a spatial conditioning tool.
Meaning what?
It maps inputs directly to pixel coordinates, which is why it works flawlessly for posing skeletons or depth maps. But a palette is not spatial. It is a global aesthetic constraint.
Oh.
If you try to force a global palette through a spatial control net, you restrict the model's ability to organically distribute the light and shadow. The cross-attention mechanism allows the UNet to dynamically decide where the colors belong based on the semantic text, while still strictly adhering to the mathematical boundaries of the palette.
The implication for dataset engineering here is staggering.
Yeah.
If you were building your own SDXL model, you can write a Python script using scikit-image to run k-means clustering on your entire dataset.
Yep.
You extract the 5-color Scilab palette for all 10,000 images, save them as tensor arrays, and train a custom conditioning layer on your model. You are literally building a steering wheel for exact brand color management.
You transition from prompting and praying to explicitly dictating the color chemistry.
But let's look at the final boss of this process. Let's say you do all of this.
Okay.
You normalize your ICC profiles, you curate with the HSV NIMA AI, you generate perfect CLIP captions, and you train your model with k-means palette embeddings. You load up your model, you type in a prompt, and the image still generates with an awful, glowing, oversaturated HDR look.
Yeah, that happens.
Why? If your dataset is flawless, why is the model still misbehaving?
Because fine-tuning a model like SDXL is like putting a new coat of paint over an existing structure. You are fighting the ghost in the machine. You are fighting the base model's inherent biases.
The ArtSmart.ai module on color theory dives into this, doesn't it?
It does. Every foundational model has a latent color fingerprint burned into its weights by the billions of images it was originally trained on.
Right, like Midjourney has a fingerprint of extreme contrast and hyper-vibrant cinematic lighting.
And Stable Diffusion natively leans toward cooler, sometimes flatter, neutral tones.
And when users encounter a model that naturally produces flat tones, their immediate reaction is to try and fix it in the text prompt by overloading it with adjectives.
Oh, yeah. They type vibrant, cinematic, glowing, masterpiece, 8K resolution, volumetric lighting, hyperrealistic.
Word salad. And what happens mathematically in the latent space when you concatenate that many conflicting semantic vectors into the cross-attention layer?
It causes a latent space collapse, resulting in what the industry calls the HDR trap.
The HDR trap.
Yeah. Each of those descriptive words pulls the UNet's denoising trajectory in a slightly different direction. The AI interprets this massive cluster of high-intensity adjectives statistically. So it tries to satisfy the condition for glowing and vibrant simultaneously across every single pixel, rather than applying localized contrast.
And the mathematical result is an image where the shadows are lifted to neon blue, the highlights are blown out to pure white, and the midtones look like plastic.
Exactly. It violates real-world color physics because the vectors are competing rather than complementing.
So if we connect this to the bigger picture, how do you counteract the base model's bias without triggering the HDR trap? The module suggests that negative prompting is actually the key, but not in the way most people use it.
No, most people just copy and paste a block of negative text like bad anatomy, missing fingers, ugly, blurry, and just leave it there forever.
Right. So how does negative prompting actually work on a mathematical level during the diffusion process?
It is based on a mechanism called classifier-free guidance, or CFG.
CFG, you see that slider in every UI.
Right. During each step of the denoising process, the UNet predicts the noise twice. First, it predicts the noise unconditionally without looking at your prompt. Then, it predicts the noise conditionally, looking at your prompt. The CFG formula takes the difference between those two vectors, multiplies it by your CFG scale, and pushes the final image away from the unconditional prediction and toward the conditional prediction.
So it calculates the direction of generic noise and steers the image in the exact opposite direction towards your text prompt.
Exactly. When you use a negative prompt, you are replacing that unconditional generic noise vector with a highly specific vector. You are telling the model exactly what to steer away from.
Oh. So if you know Stable Diffusion has a bias toward washing out colors, and you try to fix it by prompting vibrant, you risk the HDR trap.
Right.
But instead, you use negative prompts like flat lighting, magenta tint, crushed blacks, HDR artifacting.
Yes. By pushing the CFG vector away from crushed blacks, the model naturally rebalances the contrast curve without you having to scream vibrant in the positive prompt.
You're using the negative prompt as a mathematical subtractive EQ to carve out space for the natural colors to breathe.
It is the equivalent of a colorist pulling down the muddy frequencies on a mixing board rather than just cranking the master volume.
Yeah, this is a great way to think about it.
By structuring your prompt, strictly say 1 lighting context, 2 dominant color cues, 1 emotional tone, and using the negative prompt as a precise counterweight to the base model's bias, you unlock the true potential of the highly engineered dataset you just built.
Okay, so what does this all mean? Let's synthesize all of this into a narrative case study. Imagine one of our listeners is sitting at their PC right now.
Right.
They have 10,000 scraped JPEGs. They have an RTX 4090. Walk us through the ultimate pipeline to turn that chaotic folder into a professional-grade SDXL fine-tune.
Okay, the very first script you run is a metadata extractor using Pillow and OpenCV. You identify the chaos, you find the Adobe RGB files, the 8-bit files, the 16-bit files.
Right.
You run a batch process to mathematically convert every single pixel array into a unified linear working space. The industry standard for this is ACEC.
ACE, the Academy Color Encoding System.
Yes. It is a linear color space with incredibly wide color primaries designed specifically for CGI and visual effects to ensure that the math of light behaves physically accurately during rendering.
So by forcing all your JPEGs into ACES, you destroy the camera manufacturer's gamma curves and establish a scientifically flat mathematical baseline.
Exactly. The canvas is now clean.
What's the next script?
You apply your contrast normalization using the CLA-HE algorithm we discussed to ensure feature extraction isn't blocked by bad lighting. Then you compute the global color statistics of your dataset.
So you're analyzing the whole batch.
Right. You plot the mean LA values and the hue histograms. You need to know the mathematical fingerprint of the data you are about to feed the machine.
And once we have the stats, we curate.
Yes, you load the open-source HSV NIMA model, you convert temporary copies of your dataset into the HSV full color space, and feed them into the pseudo-Siamese network.
The automated AI art critic.
You calculate the Earth mover's distance for every image, extract the predicted human aesthetic score, and automatically delete the bottom 20% of your dataset. You have just removed all the mathematically corrupted, noisy, and unappealing data.
So we are left with, say, 8,000 pristine images. Now for the semantics.
You generate highly descriptive text captions for every image, ensuring the language specifically describes the lighting and colors to perfectly align with the CLIP contrastive loss space.
And at the same time.
Simultaneously, you run a scikit image script to perform k-means clustering in the Scilab color space on all 8,000 images, extracting the 5-color mathematically dominant palettes.
And you save these palettes as tensor arrays alongside your text captions.
Correct.
And finally, the training loop.
You structure your PyTorch training script to accept the modified cross-attention inputs for both the CLIP text embeddings and the k-means palette embeddings. You fine-tune the SDXL UNet, but importantly, you don't just guess if it worked. You validate it scientifically.
How do you mathematically prove that this insane amount of dataset engineering actually resulted in a better AI model?
You generate test images and measure them against ground truth professional images using perceptual metrics. Specifically, you calculate the delta E.
Define delta E for us.
Delta E is a mathematical formula that calculates the Euclidean distance between two colors in the CLAB color space. Specifically, the CIE 2000 formula, which accounts for the nonlinearities in human eye perception.
Okay.
A delta E of 1.0 is the smallest color difference the human eye can perceive. By measuring the delta E between your generated images and your target brand colors, you can objectively prove how accurate your palette embeddings are.
You also measure structural integrity, right?
You compute the LPIPS score, learned perceptual image patch similarity.
Which does what, exactly?
Instead of just doing a dumb pixel-to-pixel comparison, LPIPS pushes the generated image and a reference image through a pre-trained VGG classification network and compares the internal feature activations. It mathematically measures how similar the images look to a human brain, accounting for texture and structure. If your dataset engineering worked, your LPIPS scores will drop significantly compared to a model trained on raw data.
This entire workflow represents a total paradigm shift.
Yeah.
Is the difference between an amateur endlessly rolling the dice, typing masterpiece 100 times, hoping the model randomly hallucinates a good image,
And a dataset engineer who dictates the exact latent chemistry of the output with scientific precision.
it requires abandoning the idea that AI art is just prompting. You are architecting the latent space from the ground up, manipulating the exact mathematical boundaries of how the machine understands light.
Exactly. It's a completely different level of control.
And that brings up a final thought for you to mull over as you start writing your Python scripts. We've just spent this entire deep dive discussing how to use k-means clustering, Scilab color spaces, and HSV-NEMA aesthetic scoring to force a machine to generate the absolute mathematically perfect image based on human consensus. But as these flawlessly color-managed, statistically flawless AI images flood the internet and become the new visual baseline for media, what happens to our own biological perception? Will reality itself, with all its bad lighting, mixed color temperatures, and muted chaotic colors, start to look wrong to the human eye? Are we teaching the machine professional color theory, or is the machine about to rewrite ours?